Hi, this is Professor Fernandez, and welcome back to Lesson 2 in the Math 205 course. We're going to talk here about Module 2 in this lesson, which is vector algebra and operations. And let's start off with this definition of what we're going to mean by adding two vectors, subtracting two vectors, and multiplying a vector by a number, a scalar. So the preamble here is let u be a vector with components u1, u2, u3, and v be a vector with components v1, v2, v3 in R3, and suppose C is a scalar. So the word scalar basically means a number. So we're thinking about C as a real number. Could be positive, could be negative, could be 0. So the sum of two vectors we are defining as this. So what does that say? Well, here's u plus v on the left, the sum of u and v. And then on the right-hand side, we have a new vector, right? Here are the brackets. And then the components of this new vector are what you would think to do naturally. So we're going to define the sum of two vectors to have components, which are the sums of the components of the vectors. Simple. And then the difference of two vectors, similarly, is going to be the new vector, whose components are the differences of the components of the two vectors. Similar idea for scalar product. A number times a vector is going to be defined as the vector whose components are scaled by that same number C. Great, so this is a very intuitive and straightforward definition in the sense of what you might expect if you're going to be adding two things and each thing is a vector that has components, or subtracting them or multiplying them by a number. Let me illustrate visually what this implies about how you add vectors. So I'm going to do it in the plane because it's a little easier to illustrate that way rather than going to R3 where it's harder to draw things in. So suppose I have a vector u here that looks maybe like this, and I have a vector, let me move it down a little bit to give myself more space. So I have a vector u that looks like this, and then I have a vector v that might look like that. So one thing I can do with this definition is I can come up with a way to visually add the vectors, if you will. How would I do that? Well, when we think about what this definition says is that the first component of the sum of the vector is going to be the component of u plus the component of v in the x direction, so u1 plus v1. So when I look at u and I look at its x component, there it is. So its horizontal component, this is u1. And when I look at v and I look at its horizontal component, there it is, that's v1. So if I'm going to add u1 plus v1, I kind of have to like move things around. So I'm going to move v so that u1 and v1 are kind of in succession. So to do that, I would have to move it roughly to there. You can see then what's happened. So now I can calculate this entire horizontal length as u1 plus v1. And that is the first component of the u plus v vector that this definition is telling me. So that's great. And then now the second component would be the sum of the y components. And by doing this movement that I just did, actually I've already made that happen. So the y component of u is here, that's u2. And the y component of v is here, that's v2. So we see here that this this vertical extent is u2 plus v2. And the definition is telling me that that is the y component of the sum. So if I now draw a new vector from the initial point of u to the terminal point of v, that new vector, I'm going to call this z. That new vector, if I write it in components, has the x component u1 plus v1. It has the y component u2 plus v2. And it's a vector. Great. So because it has the same components, it's going to have the same length as u plus v vector. And it points in the same direction as u plus v vector because the components are exactly the same. So if I found the slope of the line that z generates, it would be the same slope as this line that we're defining as u plus v. In other words, I'm trying very hard to convince you that z is u plus v, based on this definition and put into R2. So what we have here is a way to add vectors visually that doesn't require this definition, but as I've tried hard to illustrate, flows from this definition. And the way is as follows. So if you want to add a vector u to a vector, v, what you do is you move the vector v so that its initial point touches the terminal point of the vector u. And then you draw the vector that goes from the initial point of u to the terminal point of v. And that vector is u plus v. So that's nice. That's a nice visual way to add vectors. So now let's illustrate the second definition and a part of the definition and the third. I'm going to do the third first, because to subtract vectors, we can think of this as adding the negative of a vector. So we're going to talk about the negative of a vector. So let's talk about that over here with C. So if I have a vector v, here it is, my vector v. This definition tells me that negative v is putting a negative in front of the components, both of the components of the vector v. Great, so if this is my vector v, and again I look at it in terms of components, here's v1, x component, here's v2, y component. I'm now going to make these negative. These are positive numbers, so I'm going to make them negative. So how do I do that? Well, I switch v2. If v2 is 7, it would become negative 7. So here's negative v2. If v1 is, 3, it would become negative 3. So here's negative v1. And then I'm going to draw the vector starting from the same initial point to what ends up being the terminal point if I go, negative v1 to the left and then negative v2 down. So I'm going to continue to move this v2 over. Oh, it moves the point, so I'm going to erase that. There we go. Great. So then, I've tried my best, even though I've obviously failed, to draw what is a vector in the complete opposite direction, 180 degrees from the vector v. This is the vector minus v. So a more skilled artist would have been able to show you that if this is the vector v, then the vector minus v is exactly in the opposite direction. We do not change the length of the vector, because notice that if I were to calculate the norm of negative v, it's the square root of the x component squared plus the y component squared. And when you square the negative 1, it goes away. So this is the norm of v. So these two vectors have the same length. They differ, though, in the fact that they point in the opposite direction of each other. And that is exactly what we mean by negative v. Great, so now that we have a notion of what negative v is, then we can talk about subtracting two vectors. So let's go back and use what we just talked about with adding two vectors to show visually how we would subtract two vectors. Great, so here is my u and v. Let's say I want to subtract them. The first thing I would do is I would calculate or draw negative v. And now I know that that is the vector which points in the opposite direction of v, but doesn't change its length. And then based on what we just talked about for adding vectors, I would put the initial point of this new vector at the terminal point of u. So various ways to do that. I'm going to move this over here, and I'm going to move this over here. And there we go. That's one way to do it. And then I draw the vector that goes from the initial point of u to the terminal point of this second vector. And this is u plus negative v, otherwise known as u minus v. Great, so that is a review or discussion, I guess, of how these three parts of this definition work together, how they imply a very visual way of adding and subtracting vectors and scaling them. So now when you look at a vector in the plane or in R3 and you see some relationships, maybe you see this relationship, you can tell that one is the negative of the other. Or you can easily add vectors in the plane using these vector addition rules, if you will. So let me go through an additional example so that we can see more of this in action. I can show you also this little applet that'll let you interact with these things. So what does this example say? Consider the two vectors u and v. So now we're working in R3. Calculate and plot 1, 2, 3 things. So let's do that first. So number 1, let's calculate u plus v. So based on our definitions, this is just the vector which results from adding the respective components together. Great, so we get, this is the sum of the x components, that is 1. And then the sum of the y components, that is also 1. And then the sum of the z components, 2 plus 1, that's 3. Great, so my new vector is 1, 1, 3. We'll visualize that in a minute, but as this makes clear, right, we can add, subtract, scale a vector without needing to visualize it. So, oops, we're still doing part 1, just 3 subparts. So let's call that b. So how about subtracting the two vectors? So here is the difference of the two vectors, and we're just going to subtract each respective component. So 1 minus 0, that's 1. 0 minus 1, negative 1. And then 2 minus 1, that's 1. Right, so that was my sum. This is my difference. There's really no reason why these would be equal. So, you might, there's no reason to expect that they're going to be the same numbers. So I wouldn't, read into the fact that this x component is the same as that one. That generally will not be true. And then let's look at part C. So how about if I scale u by negative 3? First, let's calculate it, and then let's talk about what it means. So u is the vector 1, 0, 2. So we just multiply in the negative 3 into each of the components. So negative 3, 0, negative 6. So that's the outcome. Okay, so what do we learn potentially from this last calculation? Well, we know that negative 1 times a vector generates a vector that's in an opposite direction. But what about this 3? What does this 3 do? Well, so that's kind of what the second part of this example is intended to get you to think about. It says verify that negative 3u is 3 times the length of u. Aha. So I'm going to calculate the length of this vector. So that's going to be the square root of the components squared. Minus 3 squared plus 0 squared plus negative 6 squared. And actually, I'm not going to do this calculation because what I want to do is I want to verify that the length of this is 3 times the length of that. So what I'm going to do is I'm going to try to, pull out 3's, if you will. So I'm going to express this as, first of all, 3 squared plus 6 squared, because the negatives, negative ones square away. And then I'm going to try to pull out some 9's perhaps, or 3's, somehow make this into the norm of u. So what can I do? Well, so this is 3 squared, which is 9, plus 6 squared, which is 36. Great. And then what can I do from here? Well, I can write this as 3 times 3 plus 3 times 12. Great, so I factor out a 3. 3 plus 12. Great. So, that just it tells me that, I have a new way to write 9 plus 36, so there's nothing special going on here. But then I realize that I have another 3 that I can factor out here. So 1 plus 4. And again, you might think, why don't you just calculate, square the norm of the two vectors and compare them? You could do that, but I'm endeavoring to show you different ways to do things. So the point is that I now have the square root of 9 times 1 plus 4, which is square root of 9 times the square root of 1 plus 4. And the square root of 9 is 3 times the square root of 1 plus 4. And this is the reason why I did all this work, because this is 3 times the norm of u. How do I know that? Well, remember that u was the vector 1, 0, 2. And the norm of u is the square root of 1 squared plus 2 squared. That is the square root of 1 plus 4, right? Which is, sorry about that. Let's see if we can get back to where we were. Roughly, yes. Great. So square root of 1 plus 4, that is exactly what's here. Okay. So again, you could have done this a variety of different ways, but at least in the meantime, we had some review of some properties of radicals, and we get to the same endpoint. So I'm going to write here, therefore, the norm of minus 3u is 3 times the norm of u. So this gives us a little bit of a sense of, if I scroll up back to our definition, of another aspect of what's going on here in this part of the definition. So not only does, if c is -1, not only does that tell us information about the direction. So if you multiply a vector by -1, it changes the direction, but otherwise keeps its length. We now know that if I use a number that's not -1, but something else, that is going to change the length of the vector that results, v. Unless, of course, I use c equals 1, and that, of course, will keep everything the same. I'm basically not scaling the vector. But we just used -3, so that was, in a way, like doing two things. First of all, negative, so that flips the vector, opposite direction. And then 3, that scales the vector. And now we know exactly by how much it scales the vector. It increases its length by a factor of 3. It makes it 3 times as long. Great, so that was sort of the main insight that was built into here, the second part of the definition. Let me now go to this applet and show you how you can visualize some of these things. So I'm just going to, I've pulled that up over here. So if you click on that link, it will take you here. This is a nifty little website where on the right-hand side, you can type in the vectors v1, v2. I haven't tried this for vectors in the plane with no z component, but it may work. Anyway, I've typed in the vectors u and v from our example here. And the nice thing is, of course, you can rotate things around. One thing to be cautious of or to be aware of is that, if we look at the vector v2, for example, 0, 1, 1, it's telling us that that's the vector here in red. So if we look at just y and z, this is supposed to have y component 1, which you can see is in the foreground of the image. So it's supposed to have z component 1. So it appears z is the vertical axis. It appears to have z component 1. It does not appear to have y component 1. And there's a similar thing going on for the blue vector here. So this side is not perfect, but it gives you a very general sense of what these vectors look like. And what's even nicer is that on the right-hand side here, it says show resultant, v1 plus v2. So if we click on that, there is the sum that we just calculated. So if we go back to our work, right, this vector looks longer than v1 and v2, and it almost seems to lie in the same plane, right? You see that the blue, the red, and the turquoise are kind of in the same plane if I look at it from that direction. But anyway, so we could compare and verify. Indeed, we're adding vectors u and v, which all have components, and when we calculate the norm of u plus v, the things that we square in that under that square root are the sums of the components of u and v. So we should expect that the length of the u plus v vector would be longer than the length of the u and v vectors. We can also click on the right-hand side here, show the difference. So there we go. There's the difference. So this one also seems to lie in the same plane. And there are all sorts of good reasons for this, but I'm deliberately not talking about that till we talk about planes in the course, which will be in a later lesson. So the whole point here is to allow you again to visualize, to kind of play around, look at things from different angles, and be able to get a better sense for what adding and scaling vectors is like. You could go over here, for example, and you can change a lot of things. So, you might want to put a negative sign, for example, over here, and then see what happens. and then click draw. And that changes a lot. So, I get a whole bunch of different vectors. And you can turn things off, obviously, and just look at the initial vectors from there. Great, so I am going to go back to the lesson that was giving you a very quick way to visualize vector addition. I'm going to erase what's down here and mention a few things before we end the video about properties of vector arithmetic. Now that we have this definition of how to add, subtract, and scale vectors, and now that we've done a quick example to get acquainted with that definition. So let's talk about properties of vector arithmetic. Properties of vector arithmetic. So there are a lot of things that the definition above here, 2.2.1, leads to. A lot of properties about vector arithmetic. These, by and large, properties mimic the properties you know about for real numbers. For example, for real numbers, x plus y is the same as y plus x. If I do 1 plus 2, it's the same as 2 plus 1. There is an analogous property for vectors. If I add two vectors, it doesn't matter which one I add first. And that should make sense in the way that we define vector addition, right? It doesn't matter if I do u plus v and then bring v close to the terminal point for u, or if I start with v and then bring u close to there. I still get, in both cases, this vector. Same vector. Doesn't matter which one I add first. So many of these properties you can convince yourself should be true based on this visual way of adding vectors. And of course, you can prove component-wise. So there are a lot of properties like this that make sense, that real numbers, satisfy, that translate over to vectors based on our definition. And actually, I would encourage you to see page 580 of the Apex Calculus book, which actually lists all these properties. I wanted to talk about three of them in particular to end the video. This is property 7 in the list of properties on that page. And the first, property 7 says that 0 times any vector is the 0 vector. The reason I want to talk about this is because it introduces a very special type of vector called the 0 vector. So the 0 vector, if we think about it in R3, is the vector whose components are all 0. Similar thing in R2 would be 0, 0, or however many dimensions you're talking about. By convention, the vector 0 is directionless, meaning we don't assign it a direction. No one's going to tell you that the 0 vector points north or points northeast. We don't assign it a direction, because if we did, then it'd be a little strange. It doesn't have any components, by which I mean all the components are 0. So how can I possibly calculate a direction from that? So the 0 vector is a very fundamental part of what the rest of the algebra of vectors is about, but we won't go into that part of the story. If you ever take a linear algebra course, then you will talk a little bit more about the role of the 0 vector and its importance. Suffice it to say, it's kind of like the number 0, right? There are all sorts of reasons why the number 0 is important and lets us do all sorts of things in math. Property 8, so anyway, to just clarify to recap, there is a thing called the 0 vector. It is defined by all the components being 0, and by convention, it's directionless. So that's the main takeaway I want you to get from property 7. Property number 8 says that when I take the norm of a vector times a number, it is the absolute value of that number times the norm of the vector. We kind of saw this already. I erased it, but when we did this, we did it by showing that the norm of negative 3u was 3 times the norm of u. That's an example of this property. This negative 3, take its absolute value, becomes 3. So that's what's going on here. And this should make sense. If c is positive, absolute value of c is just c. So if I scale the vector v by c, take its norm, what I get should be longer by a factor of c than the original vector. If c is negative, then what I get, since I'm talking about the length of the vector, should be positive. So somehow the negative should go away. So that kind of explains the reason for the absolute value. Anyway, you can easily, like I said, prove all of these properties using the component version of the vector, but I keep wanting to connect them to the visual ways and language that we use. So property 9, the last one I'll talk about, is if the norm, or I should say the norm of a vector is 0, if and only if the vector is 0. This is an expression, a sort of a part of math that may be new to you. Oops, I meant to circle the whole thing, to square the whole thing, if and only if. So this is a by implication, a double implication. This means that there are two statements being made here. The first one is that if the norm of a vector is 0, then the vector itself is 0. And I should probably use the same letter. There we go. And the second one is the other way. So if the vector is 0, then its norm is also 0. Both of these should make sense in an intuitive way. If I'm talking about the 0 vector, here's an example, then of course, if I add all the components squared, I would get 0. So that makes sense. This one is a little less sense-making, if that is a word, but it should also make sense. If I look at a vector with 0 length, and I noticed that I want to change things here. The length is a number, not a vector, so I'll remove that vector symbol. So if I look at a vector whose length is 0, it must be the 0 vector. As soon as I change any one of these components to be a non-zero number, I will get a non-zero length. So again, you can prove these using components, but the intuition hopefully is developing as we talk through these properties. Actually, this property you are asked to prove in the practice problems, as well as property number 8. So that should give you the other side of this exposure, being able to do these sorts of proofs using components. Great, so the takeaways from this lesson are that we now have visual ways to add vectors, right? That was this whole process of adding vectors this way. We have visual ways to think about the negative of a vector, and we know that scaling a vector just changes its length. And we also have developed ways to think about properties of vectors. So most of the properties, as you'll see in that page 580 in the book, mirror what we know for real numbers. There are some strange-ish ones, like the fact that the 0 vector is directionless. That's a convention. But I encourage you through the practice problems to work through some of these properties. So again, you get used to using the properties of vector addition, subtraction, and scaling that we talked about in this video. Great, so I will see you in the next module.